How do you fall off a lake? You think you
Wait.
could fall off a lake?
Oh, so you think that there's like land all along the sides of the oceans?
Well, water takes the shape of its container. So in order, like if there was water, like if water could fall off the side, then there would be no water because it would all just fall off. It would have fallen off by
Right.
now.
Yeah, that's why I'm asking. Like,
But
what
it's not a
stops
disc
it?
in outer space.
So what is it? I'm sorry, you said it's on a disc in outer space.
Cartoon. I'm not saying like, oh, it's a flat Earth, but there's all these other planets, and the flat Earth is going around the sun. It's like that whole entire cartoon is fake. So we're not. There's not outer.
What?
So
space.
what you're
so
saying
like,
was disproven thousands of years ago using a camel, 2 wells, and measuring footsteps. So if you
Eratosthenes.
what? No.
Yeah.
So
sticks and shadows.
So
Yeah,
if you
that was
have
the
a well
little
in one
candle
time
through
zone
the-
and a well in another time zone, and you pay someone to tell you when the reflection of the sun is directly over one of the wells, and then you count the camel steps to the next well, and then you look at what time the sun is reflecting in that well, you can see that the sun was overhead in the wells at 2 different time points, which tells us that we have an arc length. And then we can measure the camel's footsteps. We can do just a little bit of high school math, trigonometry, and we can approximate the circumference of the Earth. And that was done thousands of years ago.
Okay, that was a good little breakdown of that. So
you can do that today. You could do that today, and people have done it, and they put the videos on YouTube
Yeah, I'm
using
aware.
bicycles and sticks.
Relax. Why don't you relax? You don't need to spiral out. We're talking about
That's where
Eratosthenes.
I'm explaining the thousands-of-year-old physics to you, which is
relax.
it's crazy that in the year 2022 we still have people doubting what like people from the
I never heard
Greek
this
era were able
before.
to figure out.
Yeah. Okay, are you done? Can you relax? Okay. You're talking about Eratosthenes supposedly measuring the radius of the Earth. So can you tell me
the radius of the Earth based on an arc length?
Yeah. Can you tell me how he accounted for refraction?
Why would he need to do that?
Oh, doesn't light bend in the air?
Well, he's doing an approximation. How much would that refraction throw the estimate off by?
So he didn't account for it.
Wait, hold on. I told you he was approximating. So how much would that throw the approximation off by?
So, do you observe parallel sun rays?
Hold on. Let's not get off of the refraction first. Can you explain the formula?
No. This is the refraction point
for the atmosphere.
I love
how that would affect the calculation.
Measuring cost
Exactly.
test. This is awesome.
Yeah.
So I'd love to hear the math.
He thinks Eratosthenes measured the radius of the Earth, but he actually didn't.
I think he approximated it based on an arc length.
Well, he didn't approximate anything. Look, he supposedly measured the Earth as a ball based on parallel sun rays and like looking at a shadow. But when you go outside, and I don't know if you've ever
that's not true.
Hold on, could you relax? I don't know if you've ever let sunlight into your house. Yeah. Okay, so you don't even know the claim, so you don't even know what you're talking about.
No, I'm saying that sun rays can't be perfectly parallel, right? Because we have distances involved, and you can measure them out. They're just going to be very close to parallel, which is why you're getting an approximation.
Right.
Is that what approximation is?
God. Have you ever let sunlight into your house through a window?
Travis, are you going to answer his fucking question?
I'm trying to answer it, but he just doesn't get the point.
No, you're giving a different example. Answer his fucking question.
What question? What an approximation is?
No, you said that the refraction would affect the estimate. I asked by how much.
Exactly, that's the question. So that's what.
Fucking answer it.
No. This is the globe question. This is what you don't understand. This is what you need to answer.
Answer his question. Yeah. Answer his question.
I'm trying to answer it, but
he can't, and he won't. He has no idea what the math behind refraction is, or what it looks like.
Okay, so just help me out. I'm trying to understand the answer to his question. So help me out.
So in order to calculate refraction, light bending around ball. Can you relax, please? Holy shit.
No, I can't. Dude, you gotta help me out.
I know, you're spiraling out. Your religion is
if you actually hold on. If you want to learn about what refraction is, what you want to do is Google Snell's law, and you can read about Snell's law, and it has to do with the angle that basically light is going to move through in different waves, and it has to do with the fluid.
The angle of incidence
light is moving through, right? Okay, so it's Snell's law. If you want to read more about it,
what's going on right now?
Actually, look at the amount of refraction that would have accounted at that experiment. It does not change the approximation at all.
Yes. Okay.
I think what's going on right now is Travis is breaking the programming that they've got, and their defense mechanisms have been trained into them are kicking in.
He's like,
There you go.
he's just trying to say something that people have been saying, like the globe proof is actually a guy with sticks from 200 years before Jesus was born.
That was the first time they did it. He approximated the
It's
right.
actually way
So,
easier to do now because
it's
any of us
exactly-
can
it
build
is- it is-
any of
the
us
point
can
is
build
no,
a
it's
rocket
not,
in our
it's not.
backyard.
Exactly.
I
Yeah. The
built
point is that this
rockets.
guy is so far
Right?
behind physics that he's literally being schooled by a dude from
Why don't
2,000
you
years
just,
ago that had 2 wells and a camel.
Why don't you just let them
No,
respond?
no.
Though?
Yeah.
But most people
guys,
don't have
Yeah,
camels.
you're
So
not-
using that as an
you
example is not super easy.
Guys, we
You're
gotta
just
let them
spiraling out,
respond
yeah.
so that we can. So then,
Sure.
and when they'll say something, and then you can respond to it, and then we'll have a conversation. Okay, great.
Yeah, they're
So
spiraling
Travis,
out.
please.
Yeah, it happens all the time because people get emotional when their religion is it's called cognitive dissonance. But
I'm religious. I
So-
just don't believe that the Earth is flat. That's all.
well, me either. You believe in the globe Earth, so that's your religious belief. I know you don't.
No,
you don't
I
get
don't.
it.
No, don't
No, I
take
have
the bait.
built-
Don't take the
Yeah.
bait.
No.
Don't take the bait.
Can I please?
I
can
have built
please
rockets.
Okay,
I've
then
sent them to
actually
space.
respond.
I've
Then-
seen a camera.
Then
Jesus
I've
Christ.
actually
It was round.
Okay, hon. Okay, so Travis, actually respond, right? Like,
All right.
go ahead, please.
Sorry. Okay. So Eratosthenes. Basically, you can show what Eratosthenes did on a flat surface, like on a flat table. If you just have like a light above a table and you have like a bunch of cups, the cups far away from the light will have more of a shadow than the cups right underneath the light. So essentially, what he did was he assumed that the sun's rays are coming in parallel because the sun's like some crazy distance away. The sun's rays are coming in parallel. So because he moves a stick really far away, like. He has a stick under the sun. There's no shadow around the stick. He walks really far away, puts another stick, and there's a shadow because the Earth's surface must
You cut out, Travis.
They got him.
mean the Earth's surface is curved, not that the
Hold
sun's
on.
rays are coming in
Travis,
at
you
all
cut
these
out.
different angles.
You
Oh,
cut out, Travis. Yeah,
sorry.
I'm sorry. Yeah, you were
well-
he just put the stick down and then he moved to the other spot. That's where you're at now.
Okay, so yeah. So basically, he just assumed that the sun's rays come in parallel, and basically, if you look at the sun and do any sort of like I could show you right now, the sun's rays do not come in parallel at all. So basically, he just kind of assumed that the Earth was a globe, and it even says that also. It says he knew the Earth was a globe before he even measured it as a globe. So he basically just assumed the Earth was a globe, looked at a shadow, and assumed that it's because the sun's rays come in parallel, which is observably, like, we never observe the sun's rays being parallel. So
never
this
fully
whole
parallel, 'cause
sun,
it's from
this whole
a sphere.
Eratosthenes looking at a shadow thing works on a flat plane the same way it would, like. Yeah.
Only if the sun is very close to the Earth, to your flat Earth, and in that
So-
point you'd be fried.
Can I explain why what he just said doesn't make any sense?
Please do.
Yeah, so none of that had anything to do with refraction. Notice the question I asked was how much would refraction affect the outcome of the approximation? And none of that he mentioned has anything to
Yeah.
do with refraction. That's number one.
Mm.
And then number two, the difference between shadows on a flat or a curved plane is easily measurable, and we can just account for that in our approximation, right? So if you're saying, oh, well, it would work on a flat plane too, you're right, the shadows would be different on a flat plane, and we can use geometry and math to measure what that would be and see which one is correct. And when you do that math, and countless people have done it, you find an arc length and you approximate the size of the Earth. It's not that difficult.
Okay, so the refraction thing. So in order to calculate refraction, which is basically talking about light bending around this ball, in order to calculate light
Not exactly,
bending around,
but okay.
What ball? Light
in order
bending
for
around
these
the sun or
observations-
light bending around the globe?
No.
Which ball?
light bending in the Earth's air,
That's
basically
close. So,
around curvature.
Yeah. So again, refraction is when light moves from one type of fluid to another type of fluid. You'll get Snell's law, which will apply. And if you want to see how that affects it, you can Google Snell's law. Of course, we use
How do
this
you
if we're
spell
going to
Snell?
SNELL. So this is
SN.
like this is the physics that you get in engineering physics 3. So this is still like first year university physics. And you do all the proofs for all this stuff. So
Yeah. So if you want to check,
DB, you want to have something? You got something to say?
Well, I'm just gonna get to bed.
Okay, thank you so
talk to
much.
you guys
man.
later.
Thanks, Doobie. Have a good one, man.
Yeah,
Damn
have a
it.
good one.
Doobie, great talking to you.
Okay, go ahead, Travis. You can respond to Snell's law.
If you wanted to, or if you want to look at watch party chat, I put some bunch of images of the sun. So in order to, because like, okay, so there's all these observations that people do that, you know, don't conform to the globe geometry, like, you know, level laser above a body of water for 20 miles, or seeing a horizon 10 miles away at 1 foot observer height. So the globe response to this is refraction. And the reason why I brought that up is actually because that's what your response will be when I show you stuff that completely debunks the globe geometry. You'll say, oh, refraction, which is hilarious because refraction by itself completely debunks the globe. But basically, in order to calculate refraction, which is, you know, it would be light bending around this ball, you need ball first. We need curved gases. So in order to calculate the light bending around the ball, yeah. Well,
so I'm sorry,
for
hold on. Are you saying that fiber
in order for
optics aren't a
ball-
thing? Like fiber optic
What do you
cables don't exist because they're not balls? Is that what you're saying?
what does cables have to do with what we're talking
He's
about?
saying you can refract without it needing to be a ball.
Right.
Yeah. Do you not understand how refraction plays
Oh,
into
so
fiber optics
you think
cables?
the Earth is flat, or
What?
wait, is the Earth flat,
oh my
or what?
goodness. No, I'm saying refraction works in multiple different types of fluid geometries.
Okay.
Do you not see why that
So,
matters?
What's your point?
All right. Oh my goodness. So
No,
you'll
please
get
tell me.
refraction whether you're on a ball or you're in a cylinder or you're on a flat plane. Refraction will exist. Snell's law doesn't like have an implication that starts off with a premise of you're on like a curved surface or something. It just has to do with fluids.
Okay, but like, if the Earth's a ball or if it's flat, then the density gradient of the gas, like the atmosphere, the air, will be like either curved or it will be flat, right?
The density
Like the air
gradient
around a
of the gas.
ball.
So the rate of change of density in air as we draw a radius from, say, the Earth's surface up until some like arbitrarily defined low pressure point that we call space, that rate of change can be arbitrarily set up, right? The first derivative of the density of the atmosphere can be arbitrary based on the mechanics and the geometry and the physics that are going on that planet. And you could set that up for arbitrarily different shapes. I don't get your point.
Aaron, this is a very accurate point that you're making, but I'm wondering, can I ask one question of our friend here? Because I'm in amateur rocketry, right? And I've made rockets and put GoPros on them, and they went up through the sky, and then the world stopped looking flat and became round, and the arc of the rocket showed us that that round thing was moving like a ball, and then it came back down, and we can see that this thing didn't just disappear into somewhere. It obviously went from place to place. So in your worldview, what happened to my rocket during that time frame?
What's the altitude that you got to?
Well, you don't have to go
Highest
very far
altitudes.
before you can see the curvature.
Well, Neil deGrasse Tyson says that you can't see curve at 128,000 feet or at 63 miles up on those Richard Branson and Jeff Bezos doing parabolic flights is too low to see the curve of the Earth. So you didn't see the curve of the Earth. It's just the lens.
That's not accurate, because there's a circle that you can see of the Earth, and as you move over it, that circle changes what's underneath it. So how is that happening?
What do you mean? There's a circle? What are you talking about?
Yeah, there's a horizon, and that horizon is always circular. But as you move, that horizon changes, and it's still circular.
Well, you're just talking about the lens, because there's like videos at extremely high altitudes that it's just a flat horizon.
If you
Like
had a 360-degree camera and you were going up through space, up above where you are, like 360 degrees from where you are now, there's Earth beneath you and sky above you, and as you get higher, the amount of Earth in that 360 gets smaller, right? And as you move through space, that Earth moves underneath you. So I'm confused as to how we managed to get to a point that there's that we can travel through space. In fact, humans can go on these rockets and see these things. Like, This is not something that rarely happens like it was in the 60s. We have people doing this all of the time. And not just like paid government shills. You could do it if you wanted to pay for it. I mean, I don't understand how you can describe something that we can observationally observe that I have done as not being real.
Okay, so is Neil deGrasse Tyson wrong when he says from 63 miles up you can't see the curve of the Earth?
What does that have to do with his question?
So he's saying he sees curve from a high altitude, but Neil deGrasse Tyson.
So you're saying if Neil deGrasse Tyson makes a claim, you believe it?
No, it's just a hostile witness.
Then why are you bringing up claims by Neil deGrasse Tyson if you don't trust him anyway?
No, so Neil is right. Neil is right.
Oh, okay.
You aren't seeing. Wait a second. You aren't seeing the globe, but what you are seeing is the Earth, and it is curved, and it forms a circle. So any perspective that you have from Earth, you cannot. Sorry, go on.
That's not what he's saying. He's not saying that. He says you can't see any curvature. He's not talking about seeing the Earth as a globe. But Rob Simmons, the guy who made the Blue Marble image, says that you can't see the Earth as a globe until you're about 1 million miles away. But that's not what Neil deGrasse Tyson is saying. He's saying you can't even see curvature from 63 miles up.
I have to leave, but before I go, I just want to throw the question out one more time. Could you explain how refraction changes the approximation of the arc length from the original question? Cool. And I'm out, guys. See you later. Appreciate it.
Thanks for coming in, Aaron. I appreciate it.
Thank you, Aaron.
Yeah, word.
Thank you.
What was the question?
Oh, it just got out. Oh, it just got
explain... Hold on.
Yeah.
Many concussions.
Yeah.
Can you? Oh, go ahead, Prime. If you.
Well, if you have the question, go ahead.
Can you explain how refraction? Oh fuck.
Refraction.
Globe.
I'm sorry. I don't have the exact question.
Damn it, Aaron. Ron.
Pause. Do you have the exact question?
We need pause on this.
Can you explain the refraction? I don't know. I'm gonna fuck it up. I'm sorry.
I think I know what. I think I know. Basically, the Earth's air density changes. So higher up, the air is less dense. So as the air moves through these different densities, as light moves through different densities, it will refract. So all you need to do to even, oh my god, this is just so much. If you check the watch party chat, I put a measurement right there. Different radius measurements of the Earth. Al-Biruni, claimed measurements. Al-Biruni and Eratosthenes, which both of them didn't account for refraction. So the refraction argument is something Globers like to bring up to try to say like, oh, this is why we can see too far because light's bending around this globe Earth. But the people who initially measured the Earth as a ball didn't account for this refraction. So it's like I show you a measurement that debunks the globe geometry, and then you try to bring up refraction, but refraction by itself is debunking the claimed geometry.
So,
I mean, I can't argue his argument, but could you answer Posh's question?
What was it? My internet cut out.
It's all right, man.
When he was talking.
Luckily, we still have here.
Let me put it a different way then. Something that might be relatable to more people. Let's say that you go on a plane and you look out the window, maybe the pilots let you up the front and you look out the window and there's a horizon all around you, forming a circle all around you. And as you move over the surface of the Earth, that horizon changes and your viewpoint, that circle that you can see, shifts. Things fall away behind you, right? That is because the Earth is a sphere, right? And we can only see a certain radius at any given time as we move around the sphere. Why would that radius exist if the Earth wasn't a sphere?
Okay. Check the watch party chat on Discord. So you're talking about seeing from high up, but I can show you like balloon footage from way higher than 35,000 feet, where it's just a
Sorry, you cut out again.
Yeah, you cut out.
Curve.
Hello? Welcome
Oh,
back.
did I? Oh, sorry.
Yeah, you cut out. You said balloon footage way
Yeah.
higher than
35,000 feet, which is
Okay.
there's balloon footage way higher than that.
Sure.
Which shows do I keep cutting out?
No, you're fine. Keep going. We'll
Okay.
let you know.
You're
Okay.
okay now.
Oh,
Now you're
now
cutting
you
out.
got it.
And now he's cutting out.
Hundreds of miles. So
yeah, now you
just
did
cut
cut
out
out. You did
before.
cut out just now.
hold on, give me 1 minute. Give me 1
Okay.
minute.
Okay.
Okay, sure.
See the light.
It's the government trying to keep him from revealing the secret.
It's like
Oh,
a
see,
light
like-
in his,
I
the
think
light in his
the
fiber optic cable isn't like working.
I think
right.
the
Not refracting
glass
properly.
the glass on the planes is just curved, and that's why we perceive it that way. You know, just saying, just saying.
Because but you can change which window you're looking at. You still see the same thing. The curvature on
It's
those
all
windows-
curved.
Okay.
It's all curved.
Give it.
No.
Travis, go ahead, please.
Okay, so there's balloon footage from way higher than 35,000 feet, which you see a level horizon from left to right for hundreds of miles. Because when something moves away from your vision, it decreases in size because it's moving away. It shrinks its angular size shrinks. So when you move above the Earth, the higher up you go, you can see more because
But
it's
what is
moving
the
away from your
horizon?
vision.
If the Earth's
Okay,
flat,
that's a good question. But so you can see at 120,000 feet. I could show you like right now a bunch, but you can see from left to right, hundreds of miles level horizon, and there should be 6,600 feet of curvature for 100 miles. Yet there's supposed to be only, like, people say there's curvature at the beach, like you can see a boat going over the curve of the Earth. Yet from left to right, it's flat, even though you can see farther from left to right. So it's like they're basically saying the Earth is curved like a cylinder, which doesn't make any sense.
have you
Yeah.
ever been out to sea on a boat?
Yeah.
Because then the same phenomena appears in all directions.
Horizon?
Yeah.
Yeah, so the horizon is the position where the sky appears to touch the ground. So basically the horizon distance will change based on the ambient conditions, the atmospheric conditions. Like, it's basically like if there's fog, you can't really see that far away. You know, you can see further or less far, based on the conditions. But the horizon is actually just the limit of your eye's ability to resolve things. So you can't read a book from like 200 feet away. If that book keeps moving farther and farther away, eventually you won't be able to see it. So
But
that's
we
what the
don't have to
horizon
rely
is.
on just eyes anymore, right? Like, we have binoculars
Exactly.
and things.
Right.
And you still reach
And
a
with
point where they can't
binoculars-
see.
Right. No. With binoculars, there should be 16 feet of curvature for 5 miles. But anybody with basic binoculars, you can just go to the beach, put the binoculars right above the water, and you could see 5 miles away. And
Where
there's
did we get
way more
16
powerful.
feet from? I'm sorry, I don't fucking know this.
The Eratos, the guy, Sticks and Shadows dude. Sticks and
Okay.
Shadows. Yeah. Who actually didn't measure. The whole point is there's this claimed geometry, but when you look into where that actually even comes from, he actually never even measured the Earth as a ball. And, well, anyways. So there's stuff way more powerful than just binoculars, like the Nikon P1000, which you could see, like I sent a GIF, which I could send the video to, of observation done in Santa Barbara of somebody at 1 foot observer height, and they zoom in on these oil platforms 6 and 9 miles away, and you could see the horizon behind both the platforms at 10 miles away. But based on the globe geometry, the horizon can only be at 1.2 miles away at 1 foot observer height. So the higher up you go, the further away the horizon's going to be. So based on the globe geometry, at 6 feet, the horizon's going to be 3 miles away. Yet this guy at 1 foot, using a zoom lens, can see a 10-mile away horizon. And there's one that's way further.
Wait a second. You just said that this was based on my eyes. So why does how tall I am affect my eyesight?
Because it's when you move above the plane, you can see more. It's just the angular size. Like, the higher up you go, you can see more.
That angular size only works if it's a circle. If it's a flat surface, then it doesn't change? What
No,
angle
no.
is changing?
Like, okay, your eyes basically form cones. Like when you look down a hallway, right? The ceiling and the floor and the walls, like they all come in. Like the ceiling will come down. Like if you look down a really long, if you look down a street, like this is how artists will like draw depth. If you look down a street, the street lights that get further away from you are appearing to descend and like come in. So when you go up, basically your perspective matrix, like the limit of your eyes and your eyes' capability, changes.
But if I'm in a hallway and I look at 1 foot, I can't see less distance than if I look at 3 foot.
So,
yeah,
quick question. You're saying that someone took a telephoto lens from the Nikon P100 at sea level and was able to see out with a clear picture at 10 miles?
Well, it's not a picture; it's a video, and it's not completely clear, but it doesn't really. It's not really affecting.
In general, at sea level, you can't see a very clear picture zoomed at very far because of the how dense the
moisture.
Yeah, because of the moisture.
That's why the longest. Right, there's more moisture over water. That's why the longest observation.
Well,
yeah.
The big problem is it causes a bunch of ghosting, which creates artifacts and makes horizons seem inconsistent. So it's not a good test. Those high-powered telephoto lenses are usually intended for looking up into the sky, so you don't have to deal with as much atmosphere.
Well, it doesn't really matter because that observation specifically is 10 times the globe. Like it's 10 times falsifying the globe geometry. So even if you want to argue any of these factors, none of them are enough to explain it away because it's 10 times. The radius would have to be 10 times bigger. But this is why the longest. What you're saying about?
Wait, how is that? Yeah, if it's ghosting and giving you. No, we're not going to be. No, we're not going to be looking up anything here. So, just kind of explain
I put
your
it in
position.
the Discord. I put it in the Discord.
Yeah, so that's apparently supposed to be
the world's longest distance observation is actually done in the desert because it's like dry. That's where you can do really long observations.
High desert, not at or below sea level. But
yeah. Sonia,
I'm looking at these photos and
hold on. I'll let Sonia go, and then we'd love to hear from you. Sonia, please.
Yeah, so I'm not sure about this. I'm not sure I actually trust it because at sea level you would have so much ghosting because this is something I've dealt with a lot. Like you go out less than a mile and you've got so much ghosting, it's a very inconsistent picture.
When you say ghosting, what do you mean?
So ghosting is effectively it's like aberrations in the picture because of how much higher density atmosphere you're having to pass visual light through in order to get the picture back. And so that causes a lot of, you're going to get two different effects. One is you're going to have a lot of refraction, which happens because of how dense the atmosphere is along sea level. But then in addition to that, a lot of light also will get absorbed and not come back, will not make it back or make it all the way into to where you are. So it's a
well, yeah, that's my claim.
Coming in for the picture.
Yeah, you're just helping you're helping it because that's exactly right. It's at sea level where you can't really see that far, and it's still 10 times too far away.
When you're going,
and the whole point is it is refraction because the horizon will move day to day. So the horizon isn't a geometric curve; it's an optical effect that changes day to day based on the conditions. So it's not curvature.
Well, when it's lighter,
so
when you've got a low pressure, when you have a low pressure weather, you can see much farther. But
exactly. But you don't really have a claim though because the horizon isn't curvature; it's refracted.
No. So I'm not sure what you're talking about there, but refraction varies depending on the wavelengths of light, right? So like lower, shorter wavelength light will pass through more moisture with less refraction, and higher wavelengths or other way around. So like infrared will get absorbed really quickly and will refract a lot and dissipate a lot, and blue light will pass through a lot more moisture in the atmosphere without as much refraction or dissipation. And
Okay.
and depending on the wavelengths, you can have more of it passing through and refracting more gradually over longer distances, which can cause a curvature of light. So it depends
but
on what
because of
wavelengths
that,
you're talking about.
yeah, because of what you're saying, like everything you're saying, there actually is no claim for a globe in the first place, though.
How?
Like if you actually
Explain
understand,
that.
yeah. So if you understand where this even comes from, the supposed curvature rate, um,
Well, why do
everything
you
that you're
think
saying,
that what I'm
yeah,
saying, explain specifically, because I just explained two things. One, that there is refraction, excessive refraction with some wavelengths, and there's a lot less refraction with other wavelengths. So explain to me how those
yeah,
two things
sure.
somehow make this
So if
debunk
you
this.
account for or if you just say that like some crazy amount of like the max amount of refraction possible, like you just guesstimate some crazy amount of refraction, uh, the max it can go at 1 foot observer height isn't even 2 miles away, the horizon. So that observation, like even if you try to say the light's bending around this ball, like refraction's, it's still way off, like it's still 10 times farther
How?
away, which no amount of refraction can explain.
Wait, how is that
Because
still off?
if you go with the max amount of refraction, like you can go to globe earth calculators and go to 120% refraction. The max amount is
120% refraction of what wavelengths?
uh,
930 nanometers? 550? 420?
I don't know. But
so then why are you even using this? Why are you even calling this a debunking of the curvature of the Earth? Because some wavelengths
it's not a laser beam. They're just doing an observation. So it's not like they're shooting.
Doesn't have to.
Yeah.
Well, so first of all,
so it's not.
Laser beam is just concentrated wavelengths of light, right? So that are all moving at the same phase. But light is a spectrum. A visible light, like what we see, which is roughly 400 nanometers to like 700 or something like that. No, less than that, I think. Okay. So that's like visual spectrum for us. And then, of course, there's still visual spectrum for other creatures with different eyes, right? Who can go much further into ultraviolet and far ultraviolet and near infrared and far infrared, etc.
Yeah. So you know what wavelengths? It's just what our eyes can perceive.
Yeah. So now, red light, which is up in the 600 range, it's going to refract much more readily through moisture, and violet, which is down in the 400 range, won't. So what is this maximum refraction you're talking about? Tell me what it is that you're talking about, because I've never heard this before. Yeah. So I'd like to know something specific and give me the wavelength that you're talking about.
Right. Well, this is the whole problem. It's if you're going to try to calculate the refraction around a ball, you need the ball Earth. You need to plug in the radius to these equations, which you don't. There is no radius. Like there's no claim for a radius of the Earth, though, which is the whole problem. Like you can't even account for refraction because there's no radius. There's no ball. So if you're going to try to account for light bending around a ball,
a pint of glass has refraction.
It's kind of I'm going to just say this. It's kind of the reason I jumped in is just because light is sort of my thing. Electromagnetic, radiation is just sort of a thing that I've focused on. So when I heard you talking about refraction and stuff, I thought, geez, it sounds like this guy's pulling this stuff out of his ass. It sounds like he doesn't know what he's talking about here. So I was trying to narrow down on that. Now I don't know much about like astrophysics. I do know a bit about both classical mechanics and quantum physics. And I know that you glossed over a lot of things there. So I wasn't sure if you wanted to go kind of back to what we were talking about, what you guys were talking about earlier with mass and gravity.
Oh, yeah. Well, astrophysics, doesn't exist because outer space doesn't exist. So it's like saying space physics, but there's no space. So
that's quite a religion you have there. But
no, astrophysics is the religion. Like I don't.
You just said it
this
doesn't
belief.
exist. You just said it doesn't exist.
You believe it exists. I don't.
Do you believe in?
Well, hold on one second. You haven't actually assessed what it is that I believe yet. So,
well, you said I have a religion when it's the opposite. So it's kind of obvious.
Because you made a claim when there's a lot of evidence to suggest to the contrary. You
it's
could
not a claim,
say
it's just
You could say that that based on the evidence that you've been presented, you don't feel a reason to take it as a conclusion. And I think that's perfectly fair. I think a lot of the stuff that's worked with is something that people don't necessarily have to take as a conclusion. But so
now outer space
are you
is
aware of
fake? Yeah, it's provably fake because the second law of thermodynamics debunks it. High pressure.
So you're working off of theories as well, right? So
no,
you say that
second law.
Why is it a law?
Because it's just what happens, and
Well,
no one had to come up with it.
Can you explain how it happens?
So high pressure moves to low spontaneously. So basically, if you have like a tire with air in it, and you pop the tire, the air in the tire goes out. High pressure moves slow. That's how your lungs work. It's how you breathe. Like when you expand your lungs, it decreases pressure. Air goes in, then you contract your lungs, increases pressure.
And
you expel air.
How does this?
So high pressure moves to low spontaneously, yet our 14 psi gas pressure atmosphere is supposedly touching the 10 to the negative 17 torr vacuum of outer space with no barrier in between. If that was the case, our air would just fill the vacuum.
First of all, it isn't. It's much thinner up there, and it gets gradually thinner as you go higher and higher up.
So vacuum gradient, you can't demonstrate a vacuum gradient, or excuse me, a gas pressure gradient touching a vacuum without a barrier, and you can't even have gas pressure gradient without containment, anyways.
Do you know why
you can't
that
demonstrate because you need a container for gas pressure.
Nope, not exactly. Do you know what gravity is?
Yeah, the bending and warping of space-time caused by mass.
Mm-hmm. And so what is mass doing?
Hold on. If I drop something, right?
Let's forget about classical mechanics. Let's go into quantum. How does mass work?
Hold on. So if I drop something,
classical mechanics are not the same as quantum mechanics.
It's okay.
Just because the way something works, the way we physically observe it.
Hold on. Relax.
Well, hang on.
So if
I'm trying to keep you on track, and you're kind of
talking about gravity. So you want to talk about gravity? Let's just.
Well, I don't want to. I don't want to.
It'll be done in like a second. Yeah, it's not going to be a pivot at all. So if I drop something, gravity is claimed to be the bending and warping of space-time. If I drop something, you need to manipulate the bending and warping of space-time as an independent variable, and manipulate that to determine that it's the cause of an object dropping. So like I drop a pencil, you need to let me remove the bendy space-time and see if the pencil still falls when I let go of it. Or
so
add more in.
You're blending two things. You're blending classical and
It's called the
quantum
scientific
mechanics.
method, and you can't manipulate the bending and warping of space-time as an independent variable.
Well, first of all, I can tell that you don't know what the bending and
relax?
warping of space-time. Hold on. No, I think you actually need to relax. You've been very condescending. So do me a big favor. Just be a little more charitable. Don't be quite as condescending. And let's both work together,
I'm not
all right?
condescending. I'm not.
Oh, you're being super condescending. But I'm willing to be chill with you.
It like that. Yeah.
I'm willing to. I've been listening to you for a while now. You've been super condescending.
No, not to you. I was condescending to other people, but not to you.
Well, yeah, but you're being condescending to me now.
Okay, so let's just move forward, please.
Anyways, you're blending two different schools of mechanics here, and you're blending completely different separate terminologies from one to the other. So dropping a ball in the physical world that you and I observe is not the same thing as how gravity works on a quantum level.
Okay, but what I was pointing out